Hello there, and welcome, weary traveler, to Sleepy Wiki. As you settle in tonight, allow your shoulders to gently drop, feeling the day's burdens soften and fade away. Let your breath become a slow, comforting whisper. Tonight, we turn our gaze upwards towards something ancient and ever-present, something that drifts across the vast expanse of our sky, holding secrets of both moisture and light. We'll explore the ethereal forms known as clouds. These silent voyagers, sometimes wispy and delicate like a painter's brushstroke, other times grand and monumental, have inspired poets and dreamers for millennia. They are the gentle architects of weather, the carriers of rain, the soft blankets that tuck the sun into bed each evening. Join me as we embark on a tranquil journey through their fleeting beauty and profound simplicity without needing to understand, only to observe and let go. If these quiet moments bring you peace, consider leaving a gentle like, or perhaps subscribing, so more weary minds might find their way to our sleepy corner of the internet. Now, let us begin our soft exploration of the cloud. Within this vast, quiet canvas above us lies a precise and elegant science that orchestrates the very existence of clouds. They seem to simply exist, soft brushstrokes painted across the blue. But beneath their tranquil appearance lies a ballet of invisible forces, a precise and elegant science that orchestrates their very existence. Tonight, let's explore the whispered secrets of how these magnificent formations actually come to be, understanding the fundamental principles that govern their birth. Imagine, if you will, the air around us as a vast, invisible ocean. Within this ocean, there's a crucial, unseen ingredient: water vapor. It's the gaseous form of water, an ethereal presence born from the patient evaporation of oceans, lakes, rivers, and even the tiny pores of plants. This water vapor is everywhere, a silent, ubiquitous dancer, waiting for its cue. It's too small to see, too light to feel, but without it, the sky would remain an empty, cloudless dome. It's like the breath of the earth itself, rising into the atmosphere, a promise of what is to come. For this invisible vapor to transform into something we can see and touch, a cloud, it needs a gentle nudge, a significant change in its environment. The most crucial of these changes is cooling. Think of a cool breath on a window pane, or the mist that rises from a chilled drink. When air, laden with water vapor, cools down to a specific temperature, it reaches its dew point. This is a magical threshold, the exact moment the air can no longer comfortably hold all its invisible moisture. It's like a quiet sigh, releasing what it can no longer contain, allowing the water vapor to transition from its unseen gaseous state into something more substantial. Now, how does air cool down in the vastness of the atmosphere? The most common and elegant way is through a process called adiabatic cooling. Imagine a warm, cheerful balloon filled with air, rising gently through the atmosphere. As it climbs higher, the atmospheric pressure around it gradually decreases. This lighter pressure allows our air balloon to expand, to stretch out and grow larger, much like taking a deep, relaxing breath. This expansion isn't happening because it's exchanging heat with the surrounding cooler air. Instead, the parcel of air uses its own internal energy to do the work of expanding. And just as a marathon runner expends energy and cools down, so too does this rising air parcel. As it expands, its internal energy decreases and its temperature drops. This is adiabatic cooling, a beautiful word meaning without heat exchange, a quiet, internal process that cools the air simply by letting it breathe and expand as it rises. It's a natural refrigeration system, silently at work, creating the perfect conditions for cloud formation. But what makes air rise in the first place? There are several gentle forces that lift these vapor-rich air parcels upwards into the cooler reaches of the sky, each with its own quiet rhythm. Sometimes, an invisible river of air, a broad and gentle breeze, flows across a wide, slumbering land, until it encounters a majestic mountain range, rising like ancient guardians. The air, with its invisible passengers, has no choice but to begin a slow, graceful ascent up the slopes. As it climbs, it experiences that peaceful, expansive cooling we just spoke of. This is known as orographic lifting, the mountains themselves acting as gentle ramps, guiding the air upwards and inspiring clouds to cling to their peaks, like wisps of a morning dream. Then there are the grand meetings of the sky, where two great masses of air, one warm and languid, the other cool and serene, encounter each other. The warm air, being lighter and more buoyant, gently glides up and over the cooler, denser air, like a warm blanket settling over a cool bed. This slow, tender embrace lifts the warm air once again into those cooler, higher realms, creating vast blankets of clouds that can stretch for hundreds of miles. This elegant ascent is known as frontal wedging, a soft collision that leads to widespread cloudiness. Picture also a vast open plain where unseen currents of air are gently drawn together from all directions, like whispers converging from across a wide meadow. As they meet, they have nowhere to go but up, piling upon each other, creating a soft upward surge. This gentle gathering, this converging flow, initiates another ascent into the cool embrace of the upper atmosphere. This coming together, this subtle crowding of air, is called convergence. A collective upward journey. And perhaps the most familiar way is the sun's warm breath. Imagine the sun's gentle rays warming a patch of earth, perhaps a sun-drenched field or a dark patch of pavement. This warmth is absorbed by the ground, which then, like a warm sigh, passes that warmth to the air directly above it. This air becomes lighter, more buoyant, and begins to rise slowly and steadily, like a warm breath ascending. This is convection. The most intuitive way air finds its path upwards, often giving rise to those fluffy, fair-weather clouds that dot our summer skies. Now, even when the air cools to its dew point, it needs a tiny, selfless helper. Imagine the water vapor as tiny, restless spirits yearning for a home. They need a surface, a microscopic anchor to gather around. These are the tiny condensation nuclei. Tiny specks of dust, pollen, sea salt from ocean spray, volcanic ash, or even microscopic bits from faraway fires. They are the silent, selfless hosts, offering a place for the water molecules to cling to and begin their transformation. Without these innumerable minuscule particles, water vapor would struggle to condense even in supercooled air, requiring a much higher level of supersaturation to form droplets spontaneously. These nuclei are the invisible architects, crucial for the swift and efficient birth of clouds. Once a water molecule finds a condensation nucleus, others quickly join, like friends gathering around a warm hearth. They transform from invisible vapor into a minuscule liquid droplet, or if it's cold enough, a tiny ice crystal. Each droplet, initially unimaginably small, only a few millionths of a meter across, begins its journey. Billions upon billions of these tiny droplets, each no bigger than a whisper, suspended gently in the air, come together to form the visible essence of a cloud. It's a miracle of numbers, where countless unseen entities combine to create something so grand and observable. And here's a subtle secret that helps clouds grow. When water vapor transforms into liquid water, it releases a tiny burst of warmth, a latent heat. It's like the air is exhaling a gentle warmth after its transformation, a hidden energy that was stored within the vapor molecules. This released heat slightly warms the surrounding air within the cloud parcel, making it even more buoyant, giving it a little extra push upwards. This gentle warmth can enhance the lifting, allowing the cloud to grow taller and more magnificent, often leading to the towering structures we sometimes see reaching for the sky. So you see, a cloud is not just a formless blob. It's a symphony of invisible forces, the gentle ascent of air, the silent cooling through expansion, the microscopic particles acting as midwives, and the whispered transformation of vapor into visible water. It's a delicate balance, a complex dance of thermodynamics and atmospheric chemistry, all unfolding quietly above us, creating the soft wonders we see in the sky. These principles, intricate and precise, determine if and how a cloud forms. But once formed, what kind of story does it tell? Does it become a wispy feather, a towering castle, or a blanket across the sky? In our next quiet moment, we'll drift deeper into the sky's artistry, exploring the many different types of clouds these principles bring to life. These clouds we've learned to understand are not merely floating formations. They are the beating heart of Earth's most miraculous and indispensable system, the global water cycle. These clouds are not just decorative masterpieces. They are the beating heart, the very lungs of Earth's most miraculous and indispensable system, the global water cycle. Imagine our planet as a magnificent living entity, constantly breathing, constantly circulating the essence of life itself. And what it breathes, what it circulates, is water. This endless journey of water, a dance as old as time, is a delicate ballet of transformation and movement, powered by the gentle warmth of our sun. It begins often, for many of Earth's precious water molecules, in the vast, shimmering cradle of the ocean. Picture millions upon millions of tiny water molecules nestled close, feeling the sun's soft touch. As the sun's energy warms the ocean's surface, these molecules gain energy, growing restless, lighter. Like spirits wanting to ascend, they gently detach from their liquid embrace and drift upwards, transforming into an invisible gas we call water vapor. This process, known as evaporation, is the cycle's grand opening act, a quiet exodus from liquid to gas, from visible to unseen. But it's not just the oceans that contribute to this skyward migration. Lakes, rivers, and even the damp soil after a soft rain release their watery essence into the atmosphere. And then there are the plants, our silent green companions. Through tiny pores on their leaves, they too release water vapor into the air, a process called transpiration. Think of it as the plants themselves exhaling, adding their gentle breath to the atmospheric river. Even from the frosty peaks of mountains, where snow and ice might skip the liquid phase entirely and transition directly into vapor, a process called sublimation. Water molecules join the invisible parade. So, the atmosphere slowly, steadily, fills with these countless invisible water molecules rising higher and higher. The air near the Earth's surface is warmer, a cozy blanket for these vapor travelers. But as they ascend, they encounter cooler altitudes. The higher they go, the more the air chills. It's like climbing a tall, invisible mountain. With every foot gained, the temperature drops. As these once energetic water vapor molecules feel the embrace of the cooler air, they begin to slow down. Their dance becomes less frantic, their individual energy less vibrant. This is where the magic truly begins to coalesce, where the invisible dream takes on a tangible form. As these water vapor molecules cool, they begin to gather, drawn together by a subtle, inherent attraction. But they need a tiny anchor, a microscopic friend to cling to. Imagine the air as a vast, invisible ballroom, and floating within it are countless specks of dust, pollen, sea salt, or even microscopic particles from human activity, so tiny they are invisible to our eyes. These are known as condensation nuclei. They are the gentle magnet for our cooling water molecules. One by one, or in small groups, the water vapor molecules begin to attach themselves to these microscopic particles. As more and more molecules join, they transition back from their gaseous state into tiny liquid water droplets, or if the air is cold enough, into delicate ice crystals. This beautiful transformation from vapor back into liquid or solid is called condensation. And when billions, trillions of these minuscule droplets or ice crystals gather together, clinging to their condensation nuclei, what do they form? They form the very clouds that drift serenely above us. Clouds, then, are not just fleeting apparitions. They are vast, ethereal cities of water, suspended high in the sky. They are the visible evidence of the atmosphere doing its incredible work. Each cloud is a temporary, living reservoir, holding an astonishing amount of water. A single, medium-sized cumulus cloud, for instance, can contain hundreds of tons of water. But their role extends far beyond merely holding water. Clouds are the raw transportation system of the global water cycle. They are the celestial ships, carried by the grand currents of the wind, sailing across continents and oceans, carrying their precious cargo from one corner of the earth to another. Without clouds, the water cycle would be largely localized. Water would evaporate, rise a little, condense, and fall back down in roughly the same area. But because clouds can travel thousands of miles, they are the essential mechanism for distributing fresh water across the entire globe. They carry the ocean's bounty far inland, delivering life-giving moisture to mountain ranges, deserts, and vast agricultural plains that would otherwise remain parched. They are the great equalizers, ensuring that water, evaporated from one place, can replenish another. As these cloud ships journey, the tiny water droplets and ice crystals within them continue to interact. They bump into each other, merge, and grow larger. Sometimes, especially in warmer clouds, larger droplets sweep up smaller ones as they fall, a process known as collision coalescence. In colder clouds, ice crystals grow by collecting supercooled water droplets, forming snowflakes. Eventually, these droplets or crystals become too heavy for the cloud's internal air currents to support. The invisible buoyancy that held them aloft gives way to gravity's gentle insistence. And then, softly, delicately, they begin their final descent. This descent is precipitation, the way water returns to earth. It can be a gentle drizzle, a drumming rain, a silent snowfall, or even the brief rattling dance of hail. Each form of precipitation is a gift, replenishing the Earth's surface waters. Once the water falls, its journey continues. Some of it soaks into the ground, becoming groundwater, slowly filtering through layers of soil and rock, sometimes surfacing as springs, sometimes flowing into underground aquifers. Other water flows across the land's surface, gathering into tiny rivulets, then streams, and finally mighty found rivers, which carve their paths towards lakes and eventually back to the ocean, completing the grand circuit. This surface flow is known as runoff. This tireless, gentle circulation of water, where clouds play the crucial role of visible transporters and temporary storage units, is what sustains all life. It purifies water naturally, constantly renewing our freshwater supplies. It regulates Earth's temperature as the phase changes of water, evaporation absorbing heat, condensation releasing it, help balance the planet's energy budget. It sculpts our landscapes, carves canyons, nurtures forests, and fills our wells. So, when you gaze up at the clouds, remember their incredible quiet work. They are the Earth's delicate water wings, carrying the essence of life on currents of air, ensuring that every corner of our world receives its share of this precious, flowing miracle. The journey of a single water molecule is a testament to the elegant design of our planet, a continuous, harmonious ballet that never truly ends, only transforms. And speaking of transformations and journeys, as water travels through the atmosphere and falls back to Earth, it experiences fascinating changes. Sometimes it falls as liquid, sometimes as solid. Our next quiet moment together, we will drift into understanding the different forms of precipitation. Having traced water's journey through the atmosphere, we now turn to the beautiful variety of forms these travelers take. For clouds are not simply clouds, but a diverse family, each with its own character and story to tell. For just as stars are grouped into constellations and flowers into families, so too are the ethereal clouds classified, allowing us to understand their silent language, and the gentle messages they carry about the world above. Imagine for a moment that the sky is a grand celestial library, and each cloud is a unique book telling its own story. For centuries, people looked up and saw only clouds. But with careful observation, much like a patient librarian organizing volumes, meteorologists began to notice distinct patterns, shapes, and behaviors. This led to a beautiful system of classification, one that helps us identify these wandering poets of the atmosphere, primarily based on two key characteristics: their shape and their altitude, how high they float above us. Let's start with their shapes, the most visually striking feature. Picture three fundamental forms, like the primary colors from which all other hues are mixed. The first are the cirrus clouds. These are the graceful high flyers, delicate as a painter's feathery brush strokes across a pale blue canvas. Derived from the Latin word for curl, or a lock of hair, cirrus clouds are indeed wispy, thin, and appear as detached white filaments. They are found at the very top of our troposphere, often above 7,000 meters, where the air is so cold that these clouds are made entirely of tiny ice crystals. They whisper tales of fair weather, though sometimes, like a distant harbinger, they can signal a change in the weather might be on its way within the next day or two. They catch the sunlight long after sunset or before sunrise, glowing with a soft, otherworldly light, like angel's hair spun from moonlight. Next, let's imagine the fluffy, buoyant shapes of cumulus clouds. Their name comes from the Latin for heap or pile, and they truly live up to it. These are the friendly cotton ball clouds of a bright summer day, often seen with flat bases and rounded domed tops. They are the playful, individual characters of the sky, often scattered, seeming to float with a joyful independence. Cumulus clouds typically form at lower altitudes, usually below 2,000 meters. These are the clouds that children often point to, seeing familiar shapes: a dragon, a sheep, a floating castle. They are the quintessential fair weather clouds, a promise of sunshine and gentle breezes, forming as warm air rises, condenses, and forms these distinct puffy individuals. And finally, for our basic shapes, we have the stratus clouds. Their name, from the Latin for layer or sheet, describes them perfectly. Unlike the distinct individual cumulus, stratus clouds are broad, flat, gray layers that cover the sky like a vast, soft blanket or a silken veil. They form close to the ground, often below 2,000 meters, and their presence can make the sky appear uniformly gray and featureless. When they dip low enough to touch the ground, we call them fog. Stratus clouds often bring a gentle drizzle, a soft mist, or light snow, a comforting hush to the world below. They mute the sun, creating a diffused, even light, like a frosted window pane, shielding us from harsh glare. So, with our three primary shapes, the wispy cirrus, the puffy cumulus, and the layered stratus, we have the foundation. But clouds, much like personalities, are more complex than just three types. We then add their altitude into the equation, further refining our understanding and creating what we call the 10 basic cloud genera. Imagine these altitude zones as different floors in our celestial library. Low-level clouds, existing generally below 2,000 meters, or about 6,500 feet, are the ones closest to us, feeling almost within reach. Here we find the common stratus we just discussed, and the fair weather cumulus. But we also discover stratocumulus clouds, a fascinating blend. Picture broad, lumpy layers, often appearing as rolls or patches, usually gray or whitish, with darker shading. They are like a vast rippled carpet across the sky, or a gentle ocean of cloud waves. They might let patches of blue sky peek through, or sometimes bring a very light drizzle, but generally they are signs of a stable, although sometimes overcast, day. And among the low clouds, the most solemn is the nimbostratus. The prefix nimbo always tells us about precipitation. So, nimbostratus is a dark, gray, often thick and uniform layer covering the entire sky, bringing steady, continuous rain or snow. It's the cloud that settles in for a long, quiet day of persistent, moderate precipitation without the dramatic outbursts of thunderstorms. It's like a heavy, wet blanket draped across the world, hushing all sounds with its persistent, gentle weeping. Moving up to the middle-level clouds, found between 2,000 and 7,000 meters, roughly 6,500 to 23,000 feet, we encounter clouds that often have the prefix alto, meaning high in Latin, but specifically referring to these mid-range altitudes. Here we find altocumulus clouds. Think of them as smaller, more numerous versions of cumulus clouds, often arranged in parallel bands or patches. They can look like rows of tiny cotton balls, a flock of sheep, or even the dappled scales of a mackerel fish across the sky. They are usually white or gray and can sometimes indicate a change in weather is approaching, though they are beautiful to behold. And then there are the altostratus clouds in this middle layer. These are like a thicker, more diffuse version of the low stratus. They form a grayish or bluish sheet, uniformly covering most or all of the sky. Through an altostratus layer, the sun or moon might appear as a dimly lit disk, like seeing it through frosted glass, casting no shadows on the ground. They are composed of both water droplets and ice crystals, and can sometimes produce light, continuous precipitation, though it often evaporates before reaching the ground. Finally, we ascend to the high-level clouds, floating serenely above 7,000 meters, or 23,000 feet. These are the coldest realms, and so all high clouds are made entirely of ice crystals. Here, we revisit our graceful cirrus clouds, but they have companions, cirrocumulus and cirrostratus. Cirrocumulus are a rare and beautiful sight. Imagine tiny white patches composed of very small rounded grains or ripples. They often appear in delicate lines or patterns, looking like tiny fish scales or a delicate lace pattern against the blue. They are sometimes called mackerel sky when they cover large portions of the heavens. Their appearance can sometimes suggest unsettled weather in the coming days. And cirrostratus clouds are like a vast, transparent, whitish veil, often covering the entire sky. They are so thin that the sun or moon can easily shine through them, but they famously produce a beautiful halo effect around the sun or moon, a luminous ring of light created as sunlight or moonlight is refracted by the ice crystals within the cloud. Seeing a halo is a beautiful, peaceful sign, though it too can sometimes precede the arrival of rain or snow within 12 to 24 hours. there is one more grand category: clouds that don't fit neatly into a single altitude zone because they grow vertically, sometimes spanning from low levels all the way into the high atmosphere. The most dramatic of these is the cumulonimbus cloud, the majestic thunderhead. This colossal cloud, often beginning as a simple cumulus, grows upwards into a towering mountain of a cloud, often with a distinctive anvil-shaped top where it hits the tropopause. These are the giants of the sky, bringing with them heavy rain, lightning, thunder, and sometimes hail or even tornadoes. They are powerful, awe-inspiring, and a testament to the immense energy at work in our atmosphere. So, you see, the sky is not just a blank canvas, but a gallery of constantly shifting art, each piece classified by its form and its position, telling us a little more about the quiet, ceaseless work of our planet's atmosphere. We've journeyed through the basic types and their homes in the sky, from the low-lying stratus to the soaring cumulonimbus, understanding that each name whispers of its characteristics and altitude. But names and shapes are only part of their story. And so, as we drift deeper into the soft, swirling mystery of clouds, our journey takes us to their very heart, a realm so small, so intricate, that it often escapes our notice, yet holds the secrets to their existence and their gentle dance across the sky. Tonight, we'll whisper about the secret life within a cloud, exploring its microphysics and its wondrous composition. Imagine, if you will, the air around us, not as an empty space, but as a vast, invisible ocean filled with countless tiny swimmers. Most of these swimmers are air molecules, of course, but interspersed among them are precious water molecules, eager to find companionship and form something beautiful. They float, they drift, they wait. But for a cloud to truly form, these solitary water molecules, even when the air becomes cool and humid, need a little help. They need an invitation to gather, a tiny, welcoming platform upon which to begin their grand assembly. This is where the magic of cloud condensation nuclei, or CCN, enters our story. Think of them as the silent, invisible architects of every cloud you've ever seen. These aren't just any specks of dust. They are incredibly tiny particles, often less than 1,000th of a millimeter across, wafting through our atmosphere. They can be grains of desert sand lifted high, or microscopic crystals of sea salt carried inland by ocean breezes. They might be the fine soot from a distant forest fire, the gentle pollen from spring flowers, or even the remnants of volcanic ash. And yes, sometimes they are the microscopic byproducts of human activity, like sulfates from industrial emissions. Each one a minuscule, unassuming starting point. These CCN are special because many of them possess a unique quality. They are hydrophilic, which means they love water. They have a natural affinity for our eager water vapor molecules. As the air cools and becomes more saturated, reaching a state we call supersaturation, meaning the relative humidity climbs just above 100%, these CCN become incredibly attractive. Picture a bustling party where everyone is looking for a dance partner, and suddenly, little pedestals appear, perfectly sized for a single dancer. The water molecules, finally having a place to settle, begin to condense onto these tiny CCN. It's a process of gentle attachment, one molecule clinging to another, slowly, steadily building up. And so, around each microscopic CCN, a tiny nascent water droplet begins to form. At first, it's almost imperceptible, just a few hundred molecules gathered. But as more and more water vapor molecules condense, drawn by the cool embrace of the air and the welcoming surface of their nucleus, these embryonic droplets begin to grow. They swell, expanding from a size just a few micrometers wide to perhaps 10 or 20 micrometers. Still far, far too small to see with the naked eye, but large enough to reflect light and, en masse, give the cloud its visible form. This initial stage of growth, driven by condensation, is like the quiet opening act of a symphony. All the droplets grow in harmony, but not perfectly so. Slight variations in the size or type of their CCN or subtle differences in their immediate atmospheric surroundings mean that some droplets grow a little faster, a little larger than their neighbors. And this tiny difference, this slight diversity among the microscopic inhabitants of our cloud, is profoundly important. Now imagine our cloud is not just a collection of water droplets. As we ascend higher into the atmosphere, where temperatures plunge well below freezing, a new chapter unfolds. Here, things become even more magical. While we might expect all the water to freeze instantly, nature has a charming trick up its sleeve. Many of these tiny cloud droplets can remain in a liquid state even when temperatures are far below 0 degrees Celsius. Sometimes down to -40 degrees Celsius. This phenomenon is known as supercooled water. It's like tiny liquid jewels suspended in an icy world, defying the laws of common freezing. But not all is liquid in these cold realms. Some special CCN, often mineral dust particles or certain bacteria, act as ice nuclei, IN. Unlike their water-loving counterparts, these IN are exquisitely designed to encourage the formation of ice crystals directly. When supercooled water molecules encounter these specific IN, or if the temperature simply drops low enough, they readily transition into their frozen crystalline form. And what exquisite forms they take! Each ice crystal, a unique hexagonal wonder, is a tiny work of art. This is where the cloud's microphysics truly takes a dramatic turn, especially in the mixed-phase clouds that contain both supercooled water droplets and ice crystals. There's a subtle yet powerful atmospheric secret known as the Bergeron-Findeisen process. It's a tale of competition, where one form of water has a distinct advantage over another. You see, ice crystals have a lower saturation vapor pressure than supercooled liquid water droplets at the same temperature. What does that mean? It means the air around an ice crystal is less full of water vapor, even when compared to air around a supercooled droplet. So, in a mixed cloud where both supercooled droplets and ice crystals coexist, a gentle stealing begins. The ice crystals, with their lower vapor pressure, act like tiny, thirsty sponges, drawing water vapor away from the surrounding supercooled droplets. The supercooled droplets, sensing this atmospheric imbalance, begin to evaporate, releasing their water vapor into the air. This vapor then rushes to condense and freeze onto the growing ice crystals. It's a beautifully efficient process. The ice crystals grow rapidly, feasting on the vapor stolen from their liquid neighbors, sometimes becoming hundreds or thousands of times larger than the liquid droplets. These burgeoning ice crystals, now significantly heavier, begin their stately descent through the cloud, often colliding with other supercooled droplets on their way down, which then instantly freeze onto their surface, further enhancing their growth. This is often the primary mechanism for precipitation, especially in temperate and polar regions. Most of the rain we experience, even on a warm day, often begins its life as ice high up in the cloud, melting into liquid droplets only as it falls through warmer air closer to the ground. But not all clouds rely on ice. In warmer clouds, where temperatures remain above freezing throughout, another process takes over: collision coalescence. Imagine our slightly varied droplets, some a little larger than others. The larger droplets, being heavier, fall a tiny bit faster than their smaller siblings. As they descend, they sweep through the cloud, gently colliding with and absorbing smaller droplets in their path. It's like a benevolent snowball effect, but with liquid water. These larger droplets grow into raindrops, patiently collecting their smaller compatriots until they become heavy enough to overcome the updrafts holding them aloft. And then they begin their journey to the earth as warm rain. So, a cloud, in its essence, is a breathtakingly complex composition. It's primarily water, in its glorious phases of liquid droplets, crystalline ice, and even tenacious, supercooled liquid. But it's also composed of those incredibly vital, almost mystical, microscopic particles, the cloud condensation nuclei and the ice nuclei, which are the very seeds of its being. And interwoven within this watery matrix are trace gases and other tiny aerosols absorbed from the air, each playing a subtle role in the cloud's chemistry and fate. It's a bustling, microscopic city, silently shaping the weather above us, where every tiny particle and every subtle shift in temperature or humidity initiates a cascade of events. The visible majesty of a cloud conceals this invisible, intricate dance, a symphony of molecular forces and tiny encounters that gives it life. And understanding this hidden world helps us appreciate the grander story of our planet's atmosphere, a story that continues to unfold as we look to the bigger picture of how clouds influence the very climate of our world. But that, perhaps, is a whisper for another moment. Having learned to recognize these different forms, we might now observe something equally wondrous. These clouds are rarely still. They journey, they drift, guided by invisible forces in a grand ballet across our vast sky. For clouds are rarely still. They are forever on the move, carried by invisible currents, guided by forces we cannot see but can certainly feel and observe. It's a dance, a majestic, slow-motion choreography performed on the grandest stage imaginable. At the heart of this movement, of course, is the wind. Imagine the air around us, invisible yet ever present, feeling a gentle push from areas where it's a little more crowded, a little denser, towards spaces where there's more room to breathe. This quiet migration, this tender drift, is what we call wind, the great sculptor and shepherd of our cloudscapes. It's not a single, uniform breeze, but a complex tapestry of currents weaving through the different layers of our atmosphere. Near the Earth's surface, The wind often feels like a soft whisper, sometimes a playful nudge, as it encounters the friction of trees, hills, and buildings. This friction acts like a gentle brake, slowing the air's onward journey, creating eddies and small localized swirls that can push a tiny wispy cloud into a brief, whimsical dance over a rooftop or across a field. Cloud. But as we ascend higher, leaving the Earth's uneven embrace behind, the winds grow steadier, often stronger, unimpeded by obstacles. Here, in the vast expanse of the troposphere and beyond, the air flows in grand, sweeping rivers, much like the ocean currents far below. These are the highways of the sky, and they transport entire systems of clouds, sometimes carrying them thousands of miles across continents and oceans. Among the most powerful of these aerial rivers are the jet streams, narrow bands of very strong winds that flow, often at speeds exceeding 100 miles per hour, high up in the atmosphere, typically between 6 and 9 miles above us. These serpentine currents, like the invisible arms of a cosmic dancer, guide the pathways of major storm systems and frontal boundaries, dictating where vast assemblies of clouds will travel. When you see a long, feathery streak of cirrus cloud stretching across the sky, seemingly never-ending, it is often riding one of these powerful jet streams, borne along at incredible speeds, though from our perspective, it appears to move with stately grace. Yet not all cloud movement is horizontal. There's a beautiful vertical dance at play too, powered by the warmth of our sun. This is the phenomenon of convection, a gentle rising of warm, moist air. Imagine a tender, slow-motion bubble of warm air, warmed by the sun-baked earth, beginning its ascent, lighter and more buoyant than the cooler air surrounding it. As it rises, it carries with it invisible water vapor. When it reaches a certain altitude, where the air is cooler, this vapor condenses into those tiny visible cloud droplets or ice crystals we discussed earlier. This process forms those fluffy, cauliflower-shaped cumulus clouds often seen on a sunny day. They grow upwards, like gentle giants reaching for the sky, their vertical movement a direct result of that warm, buoyant air lifting them. And as warm air rises, cooler, denser air sinks to take its place, creating a continuous, circulating current, a slow, atmospheric breathing that helps shape and move clouds from the ground up to their highest points, sometimes even developing into the towering, majestic cumulonimbus clouds of thunderstorms. Now, add another subtle but profound influence to this celestial choreography: the Earth's own spin. Our planet is constantly rotating, a gentle, silent turn that might seem imperceptible to us, but which has a profound effect on anything moving freely across its surface, including vast air masses and the clouds they carry. This is known as the Coriolis effect. It's like an invisible hand, gently deflecting moving objects, to the right in the northern hemisphere and to the left in the southern hemisphere. This isn't a force that creates wind, but rather one that modifies its direction, guiding those grand rivers of air, and thus the cloud systems within them, into immense swirling patterns. It's why you see those colossal, graceful spirals of clouds on satellite images, particularly around low-pressure systems, as the air gets gently nudged into a turning motion as it flows towards the center of the low. Topography, too, plays its part in this intricate dance. Imagine a mighty mountain range rising like an ancient spine from the earth. As wind-driven air encounters this colossal obstacle, it has nowhere to go but up. This forced ascent, known as orographic lift, cools the air, causing the moisture within it to condense and form clouds, often draping the mountain peaks in misty veils or creating dramatic banks of cloud along their windward slopes. This is why certain mountain ranges are perpetually cloudy or rainy on one side, while the other side, in what's known as a rain shadow, remains dry and clear. Sometimes, as the air flows over the mountain and descends on the leeward side, it can create exquisitely beautiful lens-shaped clouds known as lenticular clouds, motionless-looking, like stacked plates or flying saucers, even though the air is streaming rapidly through them. These are a visible testament to the air's wave-like motion as it interacts with the Earth's contours, a silent declaration of the mountain's power to sculpt the sky. These vast movements are also driven by the fundamental ebb and flow of atmospheric pressure. Areas of high pressure, where air is sinking gently and spreading outwards, tend to bring clear skies and calm conditions, as the descending air discourages cloud formation. But as air flows away from these high-pressure zones, it moves towards areas of lower pressure, where air is generally rising. These low-pressure systems are the great gatherers of clouds, drawing air inwards in a gentle, swirling embrace, lifting it and encouraging condensation. This is why low-pressure systems are often associated with extensive cloud cover, rain, or snow, as they effectively act as a giant vacuum cleaner for moisture-laden air, collecting clouds and moving them in vast cyclonic patterns across the landscape. The very breath of our planet, inhaling and exhaling, dictates the grand pathways of these cloudy processions. And then there are the majestic encounters between different air masses, known as fronts. Imagine two colossal, slow-moving oceans of air, one perhaps cool and dense, the other warm and moist, gently approaching each other. When a warm front arrives, the lighter, warmer air gently glides up and over the cooler, denser air ahead of it. This long, gradual ascent creates a distinctive sequence of clouds. First, the high, wispy cirrus, then the thicker altostratus, followed by the deep, rain-bearing nimbostratus. It's a slow, stately procession of clouds, often bringing hours of gentle, steady precipitation. A cold front, on the other hand, is a more assertive meeting. The denser, colder air pushes beneath the warmer air, forcing it upwards more rapidly. This more vigorous lift can lead to the formation of towering cumulus and cumulonimbus clouds, often bringing shorter, more intense bursts of rain or thunderstorms. Each type of front has its own characteristic parade of clouds, a specific signature etched into the sky by these grand atmospheric encounters. Globally, these movements are part of even larger slow-motion engines, the Hadley, Ferrel, and Polar cells, vast circulation patterns that govern the prevailing winds across our planet. These immense, unseen wheels of air determine the primary direction clouds will travel over vast regions, ensuring that moisture is distributed around the Earth in a continuous, rhythmic cycle. From the trade winds that carry clouds across the tropics to the westerlies that guide weather systems across temperate latitudes, these global cells are the ultimate choreographers of the sky, ensuring that clouds are not just moving, but participating in a truly planetary rhythm. So, as you gaze up at the sky, remember that every cloud is a silent traveler, a graceful dancer propelled by unseen forces. It is a testament to the dynamic living nature of our atmosphere, where wind, temperature, pressure, and even the Earth's spin conspire to create an ever-changing masterpiece above us. Each swirl, each drift, each towering ascent is a story of motion, a narrative written in vapor across the endless blue. And with this understanding of their grand journeys, we arrive at a natural question. How do these traveling clouds release their precious cargo back to Earth? These traveling clouds, carried by wind and current, hold within them a wondrous tension. How does water, suspended so gracefully above us, ever decide to come back down? How does a cloud, so ethereal and light, release its gentle embrace and gift us with rain or snow, or perhaps a glittering layer of ice? This beautiful transformation is what we call precipitation, and it unfolds through fascinating, intricate processes, each a silent ballet performed high in the sky. Imagine, for a moment, two distinct worlds within our clouds, though they often intertwine. Our first world is one of warmth, a place where temperatures generally stay above freezing. These are often the fluffy, benevolent cumulus clouds we see on a summer's day, or the expansive stratocumulus blankets. Here, precipitation often begins with a process aptly named collision coalescence. Picture a bustling nursery filled with countless tiny cloud droplets, each no bigger than a speck of dust, born from water vapor condensing onto microscopic particles in the air. Most of these droplets are incredibly small, almost identical, like a field of tiny, shimmering dewdrops. But, as with any group, there are always a few outliers. Some droplets, perhaps fortunate enough to form around a slightly larger dust particle, or to have spent a little more time growing, find themselves a tiny bit plumper than their siblings. Even this minuscule difference, this slight advantage in size, bestows upon them a remarkable ability. Gravity, that unseen hand guiding everything, begins to pull these slightly larger droplets downwards. Think of it like a gentle, slow-motion ballet. These plumper droplets, now falling ever so slightly faster than their smaller companions, begin to encounter them on their descent. It's not a violent crash, but a soft, graceful interaction. They collide. And when they collide, they often coalesce. They merge. It's as if two tiny liquid magnets have gently touched and become one, forming a slightly larger, even more capable droplet. This newly enlarged droplet, now heavier, falls a little faster still, gathering momentum and increasing its chances of encountering even more of its smaller brethren. It's a beautiful, self-perpetuating cycle, like a tiny snowball rolling down a hill, growing with every flake it encounters. Each collision adds a little more mass. Each coalescence makes it a little stronger, a little more formidable. This dance of growth continues tirelessly within the cloud. The droplet gathers more and more moisture, accumulating countless smaller partners. Slowly, steadily, it transforms from a microscopic cloud droplet into a nascent raindrop. There's a critical point, a threshold, where a droplet becomes too heavy for the cloud's gentle updrafts to hold it aloft, too substantial for the air resistance to keep it suspended. At this moment, it overcomes these forces and begins its final journey earthward, descending as a fully formed raindrop. This warm cloud process is especially prevalent in tropical regions, where cloud bases are often warm and the air is thick with moisture, allowing this gentle accumulation to flourish, bringing forth the refreshing afternoon showers that nourish sun-kissed lands. But what about those clouds that climb much higher, reaching altitudes where the air bites with a chilling cold, where temperatures plummet far below freezing? Here, a different, almost magical process takes center stage, known as the Bergeron-Wegener process, or simply the ice crystal process. This world is a fascinating paradox, a place where water can exist in two very different forms side by side. As tiny supercooled liquid water droplets, which defy expectations by remaining liquid even at temperatures far below 0 deros, and as delicate embryonic ice crystals. The secret to the Bergeron-Wegener process lies in a subtle yet profound difference between these two forms of water. Scientists have discovered that the saturation vapor pressure over ice is lower than that over supercooled water at the same sub-freezing temperature. In simpler terms, ice crystals are thirstier for water vapor than supercooled water droplets are. Imagine the air within the cloud holding a certain amount of water vapor. If both supercooled water droplets and ice crystals are present, the air is often supersaturated with respect to ice, but perhaps only saturated or even slightly undersaturated with respect to the supercooled liquid water. This creates an invisible constant migration. Water vapor molecules, ever restless, begin to drift away from the surface of the supercooled water droplets. They are drawn, like tiny seekers of solace, towards the surface of the ice crystals, where the thirst for vapor is stronger. Upon reaching the ice crystal, these water vapor molecules don't condense into liquid. Instead, they deposit directly onto the ice, adding to its structure. This is a powerful, elegant form of alchemy. As the ice crystals grow, the supercooled water droplets, losing their precious water vapor, begin to evaporate, slowly shrinking away, sacrificing themselves to fuel the growth of their crystalline neighbors. The ice crystals, now fed by a constant stream of water vapor stolen from the evaporating liquid droplets, grow remarkably fast. They morph from minuscule specks into intricate, six-sided wonders, the beautiful, unique snowflakes we all marvel at. These growing ice crystals then become heavy enough to begin their descent. What happens next depends entirely on the temperature profile of the air layers they encounter on their long fall to the ground. If the entire column of air from the cloud to the surface remains below freezing, our delicate ice crystals will reach the earth as snow, blanketing the landscape in a soft, white embrace. But often, as they fall, they might encounter a layer of air that has warmed up, rising above the freezing point. In this scenario, the snowflakes melt, transforming into liquid-on rain before they reach the ground. It's a profound realization for many that a significant portion of the rain we experience in temperate regions actually began its life as a snowflake, high in the colder reaches of the atmosphere. There are other fascinating variations too. If the melted raindrops then fall through a deep layer of freezing air near the surface, they can refreeze into tiny pellets of ice, which we call sleet. These bounce off surfaces with a distinctive tap, tap, tap. And sometimes the melted raindrops fall through only a very shallow layer of sub-freezing air right at the surface, freezing on impact with trees, cars, and roads, creating a treacherous, glassy coating known as freezing rain. Each of these forms of precipitation is a testament to the complex journey of water through the atmosphere, a precise dance of temperature and phase change. So whether through the gentle merging of droplets in a warm summer cloud, or the elegant transformation of vapor into ice in the frigid heights, clouds are constantly at work, preparing their gifts for the world below. But before these droplets can even begin their journey, before a cloud can form at all, something microscopic must happen first. We've witnessed how clouds release their moisture as rain and snow, but now let us peek behind the curtain of their very birth to understand the tiny, often invisible architects that help bring these magnificent formations to life. Aerosols. Imagine, if you will, the vast, invisible ocean of air that surrounds our world. Within this ocean, floating silently, are countless microscopic particles, specks of dust from a distant desert, tiny crystals of salt from the ocean's breath, wisps of soot from a faraway fire, or even microscopic bits of pollen carried by the wind. These are our aerosols, the unsung heroes of cloud formation. So minute, they can dance on air currents for days or even weeks. They are truly the hidden ingredients in the recipe for every cloud you've ever admired. For water vapor, that lightest, most ethereal form of water, to gather itself into the cozy embrace of a cloud droplet, it needs a little help, a tiny anchor, a place to begin its transformation from invisible gas to visible liquid. It's a bit like a shy guest at a party, needing a friendly face to introduce them before they can truly relax and join in the fun. This is where aerosols step in, playing their most crucial role. Many of them are what scientists lovingly call cloud condensation nuclei, or CCN for short. Think of them as the tiny, invisible seeds upon which cloud droplets are born. Without these minuscule seeds, water vapor would struggle to condense into liquid droplets, even when the air is supersaturated, overflowing with moisture. It would be like trying to build a house without a foundation, or trying to start a pearl without a grain of sand. The water molecules need that little surface, that tiny scaffold, to cling to coalesce around, to grow from. Each cloud droplet, in its very essence, has a tiny aerosol at its heart, its invisible starting point. This quiet, fundamental interaction is the heartbeat of cloud formation, a testament to the power of the smallest things. Now, let's consider the fascinating ripple effect of how many of these tiny seeds are present. Imagine our cloud-forming atmosphere having a fixed amount of water vapor available, a certain volume of liquid water patiently waiting to become a cloud. In a pristine, unpolluted sky, where CCN are few and far between, the available water vapor would gather around these scattered, lonely seeds. Each droplet would have ample water to grow large and robust, like a few well-fed children enjoying a large feast. These fewer, larger droplets would shimmer softly, making the cloud appear a certain shade of white, reflecting some of the sun's gentle light back into space. This is a quiet, natural beauty. But what happens when the number of these invisible seeds increases dramatically? perhaps from human activities like industry or burning fossil fuels, which release a multitude of new aerosol particles into the atmosphere. Now, that same amount of available water vapor has many, many more seeds to condense upon. Suddenly, the feast is divided among countless new guests. Instead of a few large, well-fed droplets, we now have a multitude of tiny, delicate droplets, each vying for its share of the water. This shift from fewer large droplets to numerous small ones has a profound visual and climatic impact. When sunlight, like a brilliant spotlight, encounters these clouds, the light interacts differently. A cloud composed of many tiny droplets presents far more surfaces to reflect and scatter sunlight than a cloud with fewer, larger droplets. It's like comparing a handful of large, smooth marbles to a vast scattering of tiny, sparkling diamonds. The tiny diamonds, though individually small, collectively reflect far more dazzling light. The result? The cloud becomes brighter, whiter, more brilliant, a shimmering veil that reflects more of the sun's warmth back into the vastness of space. Scientists call this phenomenon the Toomey effect, or the cloud albedo effect. Albedo simply refers to how much sunlight a surface reflects. A brighter cloud, with a higher albedo, acts like a grand celestial mirror, sending more solar energy away from Earth. This has a cooling effect on our planet. A subtle but significant way, these tiny aerosols can influence our global thermostat. It's a reminder of how even the most microscopic changes can have macroscopic consequences for our world. But the story of aerosols and clouds doesn't end with brightness. There's another chapter, equally important, about the life and death of a cloud and how it delivers its precious cargo, rain. This is known as the Albrecht effect, or the cloud lifetime effect. Think of those numerous tiny droplets we just discussed, born from a crowded sky of aerosols. Because they are so small, these droplets are less likely to collide with one another and merge into larger drops. Imagine a bustling ballroom filled with tiny dancers. It's harder for any two to bump into each other and become one larger dancer. In clouds, this means the process that leads to precipitation, the growth of droplets until they are heavy enough to fall as rain, is significantly slowed down. Large droplets, having fewer neighbors, grow quickly and fall readily. They are like confident, swift messengers, eager to deliver their message to the ground. But many small droplets are like hesitant, tiny whispers, lingering in the air, not quite heavy enough to make the journey downwards. This can effectively suppress or delay precipitation. Clouds laden with these smaller, more numerous droplets may persist longer in the sky, reluctant to release their moisture. They become lingering guests, staying longer than anticipated. A cloud that lives longer in the atmosphere, especially a brighter cloud, continues its work of reflecting sunlight, amplifying that cooling effect we just explored. So, aerosols not only make clouds brighter, but they can also make them last longer, further influencing the Earth's delicate energy balance. It's a double influence, an unseen hand gently nudging the planet's climate in complex ways. And as if this wasn't intricate enough, some aerosols have an even more specialized role, particularly in colder regions or higher altitudes where temperatures dip below freezing. Here, water droplets can exist in a supercooled state, remaining liquid even at temperatures several degrees below zero. It's a magical defiance of the usual rules, like water holding its breath against the chill. For these supercooled droplets to finally freeze and form ice crystals, they often need a very particular kind of aerosol, an ice nucleus, or in. Dust particles, certain types of pollen, or even fragments of bacteria can act as these unique ice nuclei, providing the perfect atomic pattern for water molecules to arrange themselves into crystalline ice. They are like tiny templates for ice, guiding the supercooled water into its beautiful six-sided frozen form. These ice crystals are critically important for many types of precipitation, especially in mid-latitudes and polar regions, where the Bergeron process, a clever dance between ice crystals and supercooled water, dominates the formation of raindrops and snowflakes. So, whether it's a gentle summer shower or a soft winter snowfall, aerosols in their various forms are often the silent orchestrators. The sheer complexity and pervasive influence of these tiny particles mean that aerosol-cloud interactions are one of the biggest puzzles, and indeed one of the largest sources of uncertainty in our understanding of Earth's climate system. Humanity, through its industries and energy consumption, has added vastly to the natural background of aerosols, creating a complex, unintended experiment on a planetary scale. We're still diligently working to decipher the full extent of this interaction, to understand how our modern world is subtly reshaping the very clouds above us. These tireless microscopic dancers, the aerosols, are the unseen hands that shape the clouds, influence their brightness, and determine their lifespan. Yet for all their delicate work, clouds can also awaken with tremendous power. We've spoken of clouds' gentle whispers, their graceful dances, the microscopic particles that seed their birth. But sometimes these gentle giants awaken with a power that can electrify the very air around them, creating one of nature's most breathtaking and awe-inspiring spectacles: lightning. Imagine, if you will, being inside a towering thundercloud, a colossal city of vapor reaching high into the heavens. It's not just water droplets up there, though they are certainly present. As these clouds grow taller and colder, reaching altitudes where temperatures plunge far below freezing, something remarkable begins to happen. Inside this frosty realm, ice crystals, much like tiny glittering diamonds, begin to form. Alongside them are supercooled water droplets, water that remains liquid even below freezing, a peculiar trick of nature. And then there's something called droplets. Droplets is a charming word for what are essentially soft, opaque pellets of ice, like tiny snowballs, formed when supercooled water droplets freeze onto existing ice crystals or snowflakes. Think of them as the plump, fuzzy residents of our cloud city. Now, here's where the magic, or rather the science, truly begins to unfold. Within the turbulent heart of a thundercloud, powerful updrafts and downdrafts create a constant swirling ballet of these different particles. Lighter, feathery ice crystals are carried aloft by the rising air currents, like tiny dancers on an updraft stage. Heavier, larger droplets particles, however, are more resistant to these currents and tend to sink or move downwards. As these particles move past each other, they don't just drift idly. They collide. They brush against one another. It's a bit like a bustling ballroom where every dance step involves a gentle yet significant transfer of energy. When these ice crystals and droplets particles collide, especially in the presence of supercooled water, a fascinating electrical exchange occurs. The general rule of thumb, though it can be a little more nuanced depending on temperature and collision specifics, is that the larger, heavier droplets particles tend to acquire a negative electrical charge, while the smaller, lighter ice crystals become positively charged. Think of it as the grapple-snatching electrons, those tiny negative subatomic particles from the ice crystals during their fleeting encounters. As this process repeats millions and billions of times within the cloud, a colossal separation of charges begins. The lighter, positively charged ice crystals, caught in the powerful updrafts, are swept towards the top of the cloud, like bright, hopeful spirits rising. Meanwhile, the heavier, negatively charged grapple particles, pulled by gravity, tend to sink towards the middle and lower regions of the cloud. The result? Our cloud city transforms into a colossal natural battery. The top of the cloud becomes largely positive, while the base of the cloud, closer to the ground, accumulates a significant negative charge. And beneath the cloud, the Earth's surface responds by developing a localized positive charge, like a mirror image reflecting the cloud's negativity, drawn upwards by its powerful electrical presence. This separation of charges creates an immense electrical potential difference, a buildup of tension, much like stretching an invisible elastic band tighter and tighter. The air, normally a very good insulator, tries to keep these charges apart. It acts like a silent, steadfast guardian, holding back the immense electrical energy. But there's a limit to what even the air can withstand. When the electrical potential becomes too great, when the tension in that invisible elastic band finally reaches its breaking point, the air can no longer hold. It breaks down. And in that instantaneous moment, the sky lights up. This breakdown often begins with what's called a stepped leader. Imagine an invisible, highly charged finger slowly, hesitantly, feeling its way downwards from the cloud's negatively charged base towards the positively charged ground. It moves in rapid, short, almost jerky steps, ionizing the air as it goes, creating a faint, invisible channel of superheated plasma. It's like an exploratory scout seeking the path of least resistance. As this stepped leader approaches the ground, the positive charges on the Earth's surface are drawn to it, rising upwards in their own luminous fingers called streamers, reaching out to meet the descending leader. The moment these two meet, the scout and the welcoming hand, is the moment of connection. And that connection triggers the main event, the return stroke. This is the brilliant flash we see, the incredibly powerful rush of electrical current surging back up the ionized channel from the ground to the cloud, neutralizing the charges. It happens so fast, faster than the blink of an eye, that our brains perceive it as a single, dazzling strike of light from the sky. It's an astronomical switch being flipped, releasing an unimaginable amount of energy, heating the air in its path to temperatures hotter than the surface of the sun in mere microseconds. And what about the sound that often accompanies this incredible display? That deep, rumbling, sometimes cracking roar we call thunder? It is a direct consequence of that extreme, instantaneous heating. When the air along the lightning channel is heated so suddenly and intensely, it expands explosively. This rapid expansion creates a shock wave, a powerful ripple effect through the atmosphere, which we hear as thunder. The closer you are to the lightning strike, the sharper the crack. The further away, the longer and more drawn out the rumble, as the sound waves reflect and refract through the environment. Lightning isn't always just cloud to ground either. The vast majority of lightning actually occurs within the cloud itself, flashing from one charged region to another. We call this intra-cloud lightning. Sometimes it flashes from cloud to cloud, a brilliant bridge connecting separate stormy masses. Each type is a testament to the colossal power generated by the simple yet profound interactions of tiny ice particles high above us. So perhaps a soft rumble in the distance might hint at this incredible unseen choreography, a reminder that even in stillness, the atmosphere is alive, performing grand feats of physics and electricity. From individual storms to the entire planet, clouds wield power on every scale. From the dramatic power of a single thunderstorm, we now step back to consider an even more profound role these ethereal wanderers play, their quiet yet monumental influence on our planet's global climate. Imagine, if you will, the Earth as a grand living entity, perpetually bathed in the generous warmth of the sun. The sun's rays, vibrant and full of energy, journey millions of miles to reach us. But not all of them make it directly to the surface to kiss the land and oceans. Before they even have a chance, many encounter the vast, shifting tapestries of clouds hanging like cosmic guardians in our atmosphere. This is where the story of clouds and climate truly begins. A tale of two seemingly opposing forces working in tandem, a delicate dance of reflection and embrace. For clouds are not mere passive observers. They are active architects of our planet's thermal destiny, holding the keys to much of its warmth and coolness. Their influence is so profound, in fact, that understanding it remains one of the greatest puzzles in the intricate tapestry of climate science. One of the most immediate and visually striking ways clouds influence our climate is by acting as colossal, gleaming shields. Think of those bright, fluffy cumulus clouds on a summer's day, or the expansive, brilliant sheets of stratocumulus that often drape themselves over vast stretches of ocean. Their dazzling white tops are not just beautiful, they are incredibly efficient mirrors. When the sun's eager rays, what scientists call short-wave radiation, encounter these bright cloud surfaces, a significant portion is simply bounced back, reflected directly into the vastness of space, never reaching the Earth's surface below. It's like a giant reflective blanket spread across parts of the globe, deflecting the sun's direct heat away. This phenomenon is known as the cloud albedo effect, and it's a powerful cooling mechanism. Without these reflective shields, our planet would absorb far more solar energy, leading to a significantly warmer world. This is particularly true for low, thick clouds, which are exceptionally good at this high-stakes game of solar deflection. They are the cool protectors, diligently guarding the surface from overheating, keeping the sun's intensity in check and offering a vital regulating touch to our planet's energy budget. Each tiny water droplet or ice crystal within these clouds acts as a miniature prism, collectively scattering and reflecting light with remarkable efficiency. Imagine countless minuscule diamonds, each catching a glint of the sun and collectively sending it back, painting a shimmering, protective canvas in the sky. This reflective power is so immense that currently, the net effect of clouds on Earth's energy balance is a cooling one, despite their other roles. But the story doesn't end there, for clouds possess a dual nature, a gentle paradox. While some clouds act as reflective shields, others behave more like cozy, insulating blankets trapping warmth rather than deflecting it. This effect is most pronounced with the higher, thinner clouds, like the wispy cirrus veils that streak across the very top of our troposphere, miles above us. These delicate, feathery formations, composed mostly of ice crystals, are often quite transparent to the incoming sunlight. They let much of the shortwave radiation pass through to warm the Earth's surface below. However, their true influence comes into play after the Earth has absorbed this solar energy and begins to radiate its own warmth back out toward space in the form of long-wave radiation, much like a warm body giving off heat. These high cirrus clouds are remarkably good at absorbing this outgoing terrestrial warmth, effectively intercepting it before it can escape into the cold emptiness of space. Once absorbed, they then re-emit some of this heat back down towards the Earth's surface, acting like a celestial duvet. This is akin to the well-known greenhouse effect, where certain gases in the atmosphere trap heat, preventing our planet from becoming a frozen wasteland. High clouds, while not gases, contribute significantly to this atmospheric warming by retaining the Earth's radiated heat. So while low, bright clouds are busy reflecting the sun's immediate embrace, high, wispy clouds are gently holding on to the Earth's own radiated warmth, preventing it from dissipating too quickly. This delicate balancing act, this intricate interplay between cooling and warming, is what makes clouds such fascinating and formidable players in the global climate system. Now, you might wonder, how do we weigh these two powerful influences? Is the Earth cooling down more or warming up more because of its clouds? The truth is, it's a complex, ever-shifting equation. Scientists spend countless hours observing, modeling, and analyzing, trying to understand this grand atmospheric accounting. The overall impact depends on so many variables: the cloud's altitude, its thickness, whether it's made of water droplets or ice crystals, its geographical location, and even the time of day or season. Currently, as mentioned, the reflective power of clouds slightly outweighs their heat-trapping effect, giving our planet a net cooling influence. They are, on balance, keeping us a little cooler than we would otherwise be. But here's where the plot thickens, and the uncertainty deepens, especially in a world undergoing rapid climate change. One of the greatest mysteries, and arguably the largest source of uncertainty in climate models, lies in predicting how clouds will respond to a warming world. This is what scientists call cloud feedback loops. Will a warmer Earth lead to more of the reflective, cooling clouds, helping to mitigate the warming? Or will it lead to more of the heat-trapping clouds, accelerating the warming? It's a profound question with no easy answer. Imagine the Earth warming slightly. This changes atmospheric stability, moisture levels, and wind patterns. How will these changes ripple through the atmosphere and alter the types, heights, and coverage of clouds? For example, if warming causes fewer low, bright, stratocumulus clouds to form over the oceans, less sunlight would be reflected, leading to more warming, a positive feedback loop. Conversely, if warming led to an increase in reflective clouds, it could create a negative feedback loop, partially buffering the initial temperature rise. Understanding these feedback mechanisms is like trying to predict the exact path of 1,000 butterflies released simultaneously in different directions. Their individual movements are influenced by so many subtle factors. Adding another layer of subtle complexity are tiny, often invisible particles floating in our atmosphere, called aerosols. These can be natural, like sea salt spray, dust from deserts, or volcanic ash, or they can be human-made, like sulfate particles from burning fossil fuels. These aerosols act as crucial seeds around which cloud droplets and ice crystals form, known as cloud condensation nuclei. More aerosols can lead to clouds with more but smaller droplets. These clouds tend to be brighter and more reflective, potentially enhancing their cooling effect. Some historical pollution, for instance, is thought to have inadvertently masked some global warming by creating more reflective clouds. It's a delicate balance where even the smallest particles can have a monumental influence on the behavior and properties of clouds, further complicating our understanding of their role in climate. The dance between atmospheric chemistry, physics, and the sheer scale of global cloud cover is intricate beyond measure. Remember that the clouds above are not just ephemeral beauties. They are key regulators of our planet's thermostat, a vast dynamic system of cool shields and warm blankets. Understanding their influence on global climate requires not just theory, but careful observation, which brings us to the art and science of reading the sky. These clouds, whose global climate influence we've just explored, aren't just abstract forces in scientific models. They are ancient storytellers, revealing secrets about the weather that awaits us, if only we learn to read them. For millennia, before the advent of complex instruments or supercomputers, humanity's earliest meteorologists were simply keen observers of the sky. They learned to read the clouds as one might read a beloved book, understanding that each shape, each shade, each subtle movement held a piece of tomorrow's narrative. It is a dance between light and moisture, temperature and pressure, an intricate ballet performed high above our heads. Imagine, if you will, the serene beauty of a summer's day. You look up, and there they are, those iconic puffy white clouds, like fluffy cotton balls scattered across an endless blue. These, my dear listeners, are cumulus humulus, the fair weather friends. Their flat bases and rounded tops tell us a gentle story. The sun has warmed the earth, creating pockets of air that rise, cool, and condense into these distinct shapes. They are a sign of stable air, of gentle updrafts, promising a day filled with sunshine and calm. They are the sky's contented sighs, assuring us of tranquility. But what if these friendly clouds begin to grow? If they start to resemble aspiring towers, reaching a little higher, becoming perhaps cumulus mediocris, or even cumulus congestus? This slight vertical growth is a whisper of change. It suggests that the air is a bit less stable, that those updrafts are becoming stronger, carrying more moisture upward. The sky is beginning to stretch, to test its limits, hinting that while the day may begin fair, there's a little more energy brewing, a potential for greater things, or greater storms. And then, when these cumulus clouds truly soar, when they become towering, magnificent castles in the sky, often dark and brooding at their bases, with anvil-shaped tops that seem to spread out horizontally against the stratosphere, these are the cumulonimbus. These colossal giants are the grand orchestras of the weather, announcing thunderstorms, heavy rain, lightning, and sometimes even hail. Their immense verticality tells us of incredibly powerful updrafts, of vast amounts of latent heat energy being released as water vapor condenses into liquid, fueling their dramatic growth. When you see a cumulonimbus, the sky isn't just speaking, it's singing a powerful aria, demanding our attention and respect, forecasting a dramatic change in the immediate hours. Now let us consider a different kind of sky narrative. Picture a morning when the sky isn't dotted with individual clouds, but rather covered by a soft, gray blanket pulled across the entire expanse. This continuous, uniform sheet is a stratus cloud. It speaks of calm, stable air, often a gentle, diffused light, and perhaps a touch of mist or light drizzle. The stratus cloud is like the sky holding its breath, a quiet, contemplative presence, suggesting that the moisture in the air is widespread but not strongly rising, creating a subdued, peaceful day. If this blanket deepens and darkens, becoming pregnant with moisture, it transforms into nimbostratus, a low, dark, formless sheet that brings steady, persistent rain or snow, often lasting for many hours. These clouds don't bring dramatic storms, but rather a patient, prolonged soaking, a gentle weeping from the heavens. Twasan, high, high above, where the air is so thin and cold that water vapor freezes instantly, we find the delicate artistry of the cirrus clouds. These are the wispy, feathery brushstrokes, the elegant commas and exclamation points against the deep blue. Made entirely of ice crystals, they look like fine horsetails or delicate strands of spun sugar. Cirrus clouds are often the first messengers from afar, appearing days before a significant change in weather, particularly the approach of a warm front. They are the scouts, the advance guard, signaling that warmer, moister air is on its way, often bringing with it a sequence of other clouds. Cirrostratus, a thin, milky veil that can create halos around the sun or moon, and altostratus, a grayish sheet that often blurs the sun, before eventually giving way to rain. Mid-level clouds, like the altocumulus and altostratus, occupy the space between the low stratus and the high cirrus. Altocumulus often appear as patches or rolls, like a flock of sheep grazing in the middle sky, sometimes signaling instability that could lead to afternoon showers. Altostratus, as mentioned, is a featureless gray to bluish sheet that often masks the sun, making it appear as a dull, bright disk. These clouds, too, speak of moisture and changing atmospheric conditions, often preceding the arrival of rain or snow from a warm front. Beyond just their shape and altitude, keen observers also learn to watch the clouds' movement, the speed at which they drift, and the direction from which they approach are vital clues. Clouds moving swiftly from the west often indicate a different weather pattern than those drifting slowly from the east. If you notice high clouds moving in a different direction than low clouds, it reveals a phenomenon called wind shear, indicating different wind patterns at various altitudes, a sign that the atmosphere is complex and dynamic, perhaps brewing something interesting. Ancient mariners and farmers, with no more than their eyes and accumulated wisdom, developed simple yet profound maxims. One of the most famous, still holding scientific truth, is "Red sky at night, sailor's delight. Red sky in morning, sailor's warning." Let's gently unravel this wisdom. A red sky at sunset, when the sun dips in the west, means that the light is traveling through a high concentration of dust and moisture particles in the western horizon, scattering away the blue light and leaving the reds and oranges for the setting sun. This suggests that the weather system, which generally moves from west to east in many parts of the world, has already passed over you, and clearer, drier air is now arriving. Thus, a beautiful, fiery sunset often heralds fair weather for the morrow. Conversely, a red sky at sunrise, with the sun emerging from the east, suggests that the clear, dry air is to your west, while the eastern sky, through which the sun's rays travel to reach you, is filled with the dust and moisture of an approaching weather system. It's like seeing the storm's fiery eye watching you from afar, making it a warning for the day ahead. Of course, our modern world has supplemented these age-old observations with incredible technology. Satellites now orbit our planet, providing a constant global view of cloud formations, tracking their evolution and movement across continents and oceans. Our vigilant eyes in the sky. Radar systems pierce through clouds, detecting precipitation within them and mapping the intensity of storms. Ceilometers use lasers to precisely measure the height of cloud bases, providing crucial data for aviation and forecasting models. This flood of data, combined with complex mathematical equations, is fed into supercomputers that run sophisticated numerical weather prediction models, allowing us to forecast weather with remarkable accuracy days in advance. Yet, even with all this technology, the fundamental principles remain rooted in observation. Every satellite image, every radar sweep, ultimately helps us understand the stories these silent poets of the sky are telling. The art of cloud gazing, once a necessity for survival, has evolved into a sophisticated science. Yet it still holds that touch of wonder, that connection to the rhythms of our planet. Perhaps you'll carry with you this newfound appreciation for the sky's silent narratives. When you look up, you might see not just clouds, but characters in a grand play, revealing glimpses of what's to come. Yet these storytellers themselves are changing, reshaped by forces larger than any single storm. Our thoughts now turn from the clouds of today to the clouds of tomorrow. For just as a river carves its path through the landscape, the changing climate is subtly, yet profoundly, reshaping the very atmosphere around us, and with it, the ethereal veils we call clouds. Imagine, if you will, our Earth as a grand living entity, always in a delicate dance with the sun's warm embrace. Clouds in this celestial ballet play many roles. Sometimes they are like brilliant white mirrors, reflecting a portion of the sun's energetic kisses back into the vastness of space. These are often the low, thick clouds, the stratocumulus and stratus decks that spread like vast, comforting blankets over our oceans, especially in the cooler regions. They are Earth's natural parasols, shielding us from intense sunshine and keeping our planet comfortably cool. This magnificent reflection is known as the cloud albedo effect, a quiet guardian against overheating. But clouds are also quite the shapeshifters, and their nature can change with altitude. High up, where the air is thin and crisp, we find the delicate, wispy cirrus clouds. These are often made of tiny ice crystals, shimmering faintly like forgotten stardust. Unlike their low-lying cousins, cirrus clouds are more like a thin, almost invisible shawl wrapped around the Earth. While they reflect a little sunlight, their primary role is to trap warmth radiating up from the surface, much like a greenhouse. They allow the sun's energy in, but then hold on to the Earth's outgoing heat, contributing to the greenhouse effect. So you see, clouds have a dual personality. They can both cool our planet and warm it, depending on their height, thickness, and composition. Now, as our world gently warms due to the increasing concentration of greenhouse gases like carbon dioxide, this delicate balance begins to sway. The air in our lower atmosphere becomes a little more stable, a bit less turbulent. Think of it like a pot of water on a stove. If the heat is low, the water stays still. If it's turned up, it starts to bubble and churn. In the atmosphere, this churning is what helps bring moist air upwards, allowing low clouds to form. But with a warming climate, certain atmospheric layers become more resistant to this mixing. It's as if an invisible lid is placed upon the lower atmosphere, making it harder for those reflective low-level clouds to form and persist. Scientists are observing, with careful eyes and sophisticated instruments, that these vital low clouds, our planet's white shields, may become less frequent or thinner in a warmer world. Less cloud cover means more sunlight reaches the Earth's surface and oceans, which absorb this energy and warm even further. This creates a powerful, positive feedback loop. Warming leads to fewer cooling clouds, which in turn leads to more warming. It's like a gentle push that slowly gains momentum, a cycle that scientists are working tirelessly to understand, as it holds one of the biggest keys to predicting the full extent of future warming. But what about those high, wispy cirrus clouds, our Earth's invisible shawls? A warmer atmosphere can hold more water vapor. It's a fundamental principle of physics, like a sponge soaking up more water when it's warmer. With more water vapor available at higher altitudes, there's a possibility for more cirrus clouds to form. If these heat-trapping clouds increase, they could further enhance the greenhouse effect, adding another layer of warmth to our planet. The exact balance between the potential loss of low cooling clouds and the potential increase of high warming clouds is one of the grandest mysteries in climate science, a puzzle whose pieces are intricately interwoven with temperature, humidity, and atmospheric dynamics. This is why clouds are often referred to as the wild card in climate models. They are so complex, forming and dissipating over scales that range from tiny water droplets to vast oceanic decks, influenced by everything from dust particles in the air to global wind patterns. Predicting their future behavior with absolute certainty is like trying to guess the shape of a dream, ever-changing, elusive, yet profoundly impactful. Scientists around the world are dedicating their lives to unraveling these complexities, using supercomputers to simulate different future scenarios, exploring every ripple and whisper of the atmosphere's response. As we look to the future, there's also a quiet whisper of human ingenuity in the air. Some minds ponder if we could one day, perhaps, intentionally influence clouds to help mitigate climate change. This realm, often called geoengineering, explores ideas such as making low clouds brighter by spraying tiny sea salt particles into the air, providing more seeds for cloud droplets to form around, thereby enhancing their reflective power, or perhaps thinning out high cirrus clouds to let more heat escape. These are profound concepts, still largely in the realm of research and ethical discussion, reminding us of the immense power and responsibility that come with understanding our planetary systems. The future clouds, therefore, are not just beautiful formations in the sky. They are central characters in the unfolding story of our planet's climate. They are delicate indicators, powerful regulators, and perhaps with careful stewardship, even potential partners in protecting our world. This quest to understand and predict their behavior drives scientists to explore new frontiers. We arrive now at a fascinating landscape, the very edge of our understanding, where scientists are tirelessly working, like quiet explorers charting new territories. This is the realm of frontiers in cloud research, a place where curiosity stretches beyond the visible, diving into the hidden processes that govern our skies and, indeed, our planet's future. Imagine, if you will, that every cloud is a grand, intricate ballet, choreographed by forces both enormous and infinitesimally small. At the heart of much frontier research lies the microscopic, yet immensely powerful world of cloud microphysics and aerosol cloud interactions. Picture the air around us, not as empty space, but as a vast, invisible ocean teeming with tiny, silent travelers, the aerosols. These aren't just dust motes dancing in a sunbeam. They are the true architects of clouds, the microscopic seeds without which the grand structures above us simply couldn't form. These particles, varying from specks of desert dust to salt crystals whispered from ocean waves to the unseen exhaust from our cities, act as what scientists call cloud condensation nuclei, CCN. Think of them as tiny, eager magnets, attracting water vapor until enough droplets coalesce around them, growing large enough to become visible as a cloud. But here's where the frontier gets truly intriguing. Not all seeds are created equal. A pristine natural environment might offer fewer, larger CCN, leading to clouds with fewer, bigger droplets, which are more likely to grow heavy and fall as rain. Now, introduce a bustling city, releasing a myriad of much smaller aerosol particles. Suddenly, the same amount of water vapor has far more tiny seeds to cling to. The result? A cloud filled with many more, but much smaller droplets. These smaller droplets are less efficient at forming rain, and they also tend to make clouds appear brighter, reflecting more sunlight. This subtle shift in droplet size, triggered by these invisible particles, has profound consequences, influencing not just rainfall patterns, but also the very brightness of our planet, a delicate dance that scientists are painstakingly mapping out. This leads us directly to another critical frontier: cloud climate feedbacks. Our planet is a living system, and clouds are its magnificent, ever-changing thermostat. Imagine a vast, shimmering blanket draped over the Earth. This blanket isn't static. It constantly shifts, thickens, or thins in response to the planet's warmth, and in turn, influences that warmth. Low-lying clouds, like the broad, flat stratocumulus blankets we often see over oceans, are excellent reflectors. They act like giant mirrors, bouncing a significant portion of the sun's incoming energy back into space, thereby cooling the Earth. Conversely, high, wispy cirrus clouds, those delicate brushstrokes across the sky, tend to let sunlight pass through but trap outgoing long-wave radiation, acting more like a greenhouse gas, contributing to warming. The great scientific challenge at this frontier is understanding how these different types of clouds will respond as our planet warms. Will the low clouds thicken, offering more cooling, or will they thin, allowing more heat in? Will high clouds become more prevalent, enhancing warming? The net effect of clouds on Earth's energy budget is a complex and finely tuned balance, and precisely predicting how this balance will shift is one of the largest sources of uncertainty in our climate models. Scientists are racing to unravel these intricate feedback loops to better understand how Earth's atmospheric blanket will adjust in the coming decades, a puzzle piece vital for our future. To peer into these complex mechanisms, researchers are constantly developing new observational technologies. Imagine the world's most sophisticated detectives equipped with tools that can see the invisible and measure the intangible. High above us, satellites orbit, not just taking pictures, but employing LiDAR, laser radar, and radar to pierce through cloud layers, giving us three-dimensional profiles of cloud structure, water content, and even the size of ice crystals and water droplets within them. Missions like Calypso and CloudSat are like tireless sky gazers, offering unprecedented views into the vertical architecture of clouds. Closer to the ground, an array of instruments, specialized radars, ground-based LiDAR, and even drones soaring into the heart of storms, provide continuous, high-resolution data, capturing the fleeting moments of cloud life from genesis to dissipation. These technological marvels are our extended eyes and ears, helping us to listen to the whispers and roars of the atmosphere. But observing isn't enough. We also need to understand and predict. This brings us to the frontier of high-resolution cloud modeling. Picture scientists as digital weavers, constructing miniature universes within supercomputers. For decades, global climate models have struggled to represent individual clouds accurately because they operate on grids too coarse to resolve their intricate, often turbulent, dynamics. Instead, they've had to parameterize clouds using simplified rules to estimate their collective effects. But at the frontier, a new generation of convection-permitting models is emerging. These are like incredibly detailed tapestries where the grid cells are so small that they can explicitly simulate the life cycle of individual storm cells, the swirling updrafts and downdrafts, the precise formation of rain and ice. This allows researchers to test theories about aerosol effects and climate feedbacks with much greater fidelity, building more accurate digital replicas of our atmospheric reality, helping us to foresee the future weather and climate with clearer eyes. And what of our ability to intervene, to perhaps gently nudge the clouds? This leads to the fascinating and often ethically complex frontier of cloud seeding and geoengineering. For decades, scientists have explored cloud seeding, a process where substances like silver iodide or dry ice are dispersed into clouds to encourage the formation of ice crystals or larger water droplets with the aim of enhancing precipitation. It's like planting a tiny catalyst in a cloud, hoping to encourage it to release its moisture. On a grander scale, some researchers are exploring solar radiation management techniques, such as stratospheric aerosol injection, which would involve dispersing tiny reflective particles into the upper atmosphere to mimic the cooling effect of large volcanic eruptions, thereby reflecting a fraction of sunlight back into space. These are profound ideas, born from our growing understanding of atmospheric processes, yet they carry immense implications, urging us to consider both the potential benefits and the unforeseen ripples across our complex planetary system. La. Finally, the frontier of cloud research isn't limited to Earth alone. As we gaze up at our own clouds, scientists also turn their telescopes and probes outward, exploring extraterrestrial clouds. Imagine clouds not of water, but of sulfuric acid on Venus, or methane on Titan, Saturn's largest moon. Mars hosts ethereal veils of water ice and even carbon dioxide ice clouds. Studying these cosmic siblings helps us understand the universal physics of cloud formation, expanding our knowledge beyond Earth's unique conditions and offering glimpses into the diverse atmospheric chemistries of other worlds. It's a reminder that the phenomenon of clouds, in all their varied forms, is a universal ballet performed across the cosmos. These frontiers, from the smallest aerosol to the grandest planetary scales, are where our understanding is rapidly expanding, where questions lead to new discoveries, and where the mystery of the skies continues to unfold. And with this, our journey through the world of clouds draws to its gentle close. And so, dear friend, let us bring our thoughts back to the magnificent, gentle wanderer we've journeyed with tonight, the cloud. Remember its quiet beginnings, not with a sudden burst, but with a patient, unhurried breath. Tiny, invisible molecules, warmed by the sun's soft caress, lifted from the sleeping waters of an ocean, a quiet lake, or even the dewy grass. They didn't race, did they? No, they drifted upward, imperceptibly at first, carried on unseen currents, each one a whisper of what was to come. A silent ascent, a gentle letting go, an embrace of the vast, open sky above. Then, as they climbed higher, remember how the world around them grew cooler, like pulling a soft blanket closer on a chilly night. These ethereal travelers, once scattered and unseen, began to draw together, not through force or hurry, but through a natural, peaceful inclination. Each molecule found comfort in the presence of others, huddling close around a microscopic particle of dust, a tiny, perfect anchor in the immensity of the atmosphere. And in that quiet gathering, in that gentle clasping, something wondrous happened. They transformed. From an invisible mist, they bloomed into the first delicate wisps of white, a new form, a new presence in the sky. It was a birth so subtle, so serene, that often we don't even notice it, until a cloud, fully formed, floats into our view, a testament to this gentle alchemy. And once born, remember how it embraced its journey, carried by the very breath of the world, the quiet currents of the wind. It didn't choose its path with intention or agenda, but surrendered to the flow, drifting east, then west, north, then south. A silent ballet across the heavens, a slow, majestic dance that speaks of patience and acceptance. One moment, a fluffy sheep, the next, a grand castle, then a whimsical creature from a forgotten dream. It changed without effort, without complaint, simply reflecting the light and shadow, the whims of the air, the time of day. Its very essence was change, yet in that constant transformation, there was an unwavering presence, a quiet steadfastness. And as it traveled, It held its precious cargo, didn't it? The life-giving water, gathered and nurtured. Sometimes it grew heavy, not with burden, but with a deep, quiet purpose. And when the time was right, it would release its hold, gently, lovingly, not in a rush, but with a slow, deliberate falling, whether as soft, life-giving rain that whispers to the thirsty earth, or as silent crystalline snowflakes that blanket the world in a pristine hush. Each drop, each flake, a return to the source, a completion of a cycle, ready to begin anew. This is the quiet wonder of the cloud, dear one. A journey of ceaseless transformation, of giving and receiving, of finding form and letting go, all with an unhurried grace. It reminds us that even the most profound journeys can be undertaken with serenity, that change is a natural, beautiful part of being, and that beauty can be found in the most ephemeral moments. Look at the clouds, and you see the sky's gentle heartbeat. They are the dreamers of the atmosphere, forever shaping and reshaping, never truly gone, only transforming, circling back, finding new ways to dance across the heavens. And now, as this journey draws to its soft close, take a page from our gentle cloud. Feel the quietness settle around you. Just like the tiny water molecules gathered into a comforting cloud, you too can find peace in drawing inward, in letting go of the day's busy moments. Let your thoughts drift, light as vapor, carried by the soft breath of your own sleepy rhythms. Allow yourself to be carried without effort or worry into the gentle currents of slumber. As you close your eyes, imagine the clouds still drifting, silently, peacefully, across the vast moonlit sky. Their journey doesn't end when the sun sets. It simply continues, softly, in the dim glow of stars, perhaps even into the quiet landscapes of your own beautiful dreams. May your night be as peaceful and as full of gentle wonder as the journey of a cloud. Sleep now, dear friend. Sleep deeply and dream sweetly. Good night.